Hello everyone, my name is Matt Sandy. I'm a program manager on the DirectX team at Microsoft. And yeah. Today I'm going to tell you about DirectX Raytracing.
That's cool.
So for today's session, I'm going to go over a quick recap of the announcement that we did on Monday, which is basically, why are we doing ray tracing now? What is it good for? Then I'm going to go into API deep dive in DXR, then tell you about some of the tools and helper libraries that we have available for it. Finally, we're going to get some guys from Seed up on stage. They're going to show you some of the really cool work they've been doing with DXR. And then I'm going to show you a bunch of links for resources about how to get started using it yourself. So first, let's talk about ray tracing. So for 30 years, pretty much almost all games use the same basic technique for rendering content to the screen, and that's rasterization. Rasterization is an embarrassingly parallel problem. It's a very efficient way for solving the visibility problem, but it has its problems. There's many techniques that you see in games today where rasterization provides a passable lie for these techniques, but you usually have to kind of bend over backwards to get decent results, and there's often edge cases that you have to worry about and make a best attempt to fill in gaps. But you can end up with some really weird artifacts. Things like dynamic shadows, environment mapping, reflections, and even global illumination. Rasterization doesn't really cut it. It's a passable technique, but ray tracing is really kind of the holy grail of producing all these techniques. So along with all these techniques, the evolution of all these techniques, we've also seen evolution of graphics hardware. From the late 90s, where we got our first taste of hardware transform and lighting, through simple and complex programmable shaders, compute shaders, and finally async compute recently with the X12. In 2018, we're finally to the point where real-time ray tracing can be a reality. And with DirectX Ray Tracing, you can start adding this to your games. So for anyone not familiar with ray tracing, it's a different technique than rasterization fundamentally to render a scene. It requires representing your scene in a 3D format, which usually you're already doing for a 3D game. But then instead of rasterizing those triangles to a 2D plane, instead you cast rays into that scene, calculate intersections, potentially cast more rays out, finally accumulate all that data and generate your final image. So going back to some of these exceptions about where rasterization fails, let's take a technique that's very common in games today, screen space reflections. So here we have our extremely photorealistic pirate ship reflected on a glistening ocean. And we have a camera that we've flattened into 2D space in the top left here. So let's say we wanted to use screen space reflections to reflect this pirate ship in the water. So in many cases, this technique will work perfectly fine. Let's say you're looking at this point on the sail. You want to reflect off the ocean into the sail up on the ship. And because you've actually rendered that point on the sail in the previous frame, you can actually query your depth buffer and your color buffer to figure out what that color is and use that for your reflection data. But there's many cases where screen space reflection will fail. For example, let's take this point here. In the reflection, you'd like to be able to see this red flag on the mast. But the red flag is actually outside of the camera view frustum, so you don't have that color data. So in fact, any content that's outside of the primary view frustum, you can't reflect that with screen space reflection because it's just not there. And even for objects that are within the view frame, you can end up with cases like this, where the bow of the ship, from the camera's perspective, you can see the top of the bow, but from the reflection's perspective, you should be able to see the bottom of the bow. But because none of the primary rays from the camera actually show the bottom of the bow, you can't do screen space reflections for those. Now, in these cases, you can do clever tricks like infilling from adjacent pixels or just rendering transparent black. But in most games, what you would end up with is if you look at the reflection of the ship in the water, you just won't see the flag at all until you move your camera up, and then suddenly the flag appears. But wouldn't it be nice if we had some way to efficiently incorporate real-time ray tracing and actually fill in those gaps with screen space reflections with real queries into the 3D geometry so that we could bring in that content? Well, that's what we've aimed to do with DirectX Ray Tracing. So before I go into the details, let's talk about some of the requirements of what we would need in a real-time ray tracing solution, kind of build DXR all together as an exercise. So first, we need a way to represent the scene geometry. Second, we need a way to trace rays into the scene and get the intersections. And third, we need to figure out a way to determine and execute the material shaders. So first, let's talk about scene geometry representations in DXR. So in DXR, scenes are represented in a concept called acceleration structures. These are opaque buffers that represent the entire scene, the 3D scene. They're constructed on the GPU, and they're represented as a two-level hierarchy. I'll go into more details of that. Now, the fundamental building block of these acceleration structures is a geometry. Now, in DXR, these come in two flavors. The first is simple triangle geometries. These are, you'd be very familiar with these. They're comprised of a vertex buffer and an index buffer. Your vertex buffer can be 32 or 16-bit float3 formats, index buffer 16 or 32-bit uints. Along with the geometry, you specify a transformation matrix as well to specify where within that instance that geometry lies. In addition to the fixed function triangle geometry, you also have the ability to specify programmable geometry. I'll get into more detail about this later, but this is defined using shader code in a shader called the intersection shader. And in the geometry itself, you would specify axis-aligned bounding boxes to represent the exterior region for which your programmable geometry lies. Now, the bottom level acceleration structure, which is the lower of the two levels of the hierarchy, this is defined by a set of one or more geometries. It's built on the GPU, and it's written to this opaque buffer format. Now, comprised of bottom-level acceleration structures is the top-level acceleration structure. The top-level structure is defined by a set of instances of bottom-level structures. It is also built on the GPU and written to another format of opaque buffer with a transformation matrix for each instance. And what this allows you to do is it allows you to have it allows the implementation to spend time optimizing the representation of the bottom-level structures, which then you can have multiple instances of that you have transformations. So for example, here we have one instance of the hull of the ship on the left, and then on the right side we have the mast and the sail, but we have two instances of that in the top-level acceleration structure. Some additional details about acceleration structures. Before you construct them, you need to request the pre-build info. Because acceleration structures can vary very dramatically in size that they require, you have to query the driver for the amount of space that you need to build. This returns a conservative result for both the result space and the scratch space. So as part of the build process, the GPU will use some scratch memory that you can then throw away, but then you also need a separate buffer to store the result into. So pre-build info tells you the conservative minimum size that you need for both of those structures. After you do the actual construction, you can then query it for post-build info, and then optionally copy that into a compacted buffer. You can also do incremental updates on acceleration structures, both at the top level and the bottom level. Top level updates are going to be for cases where you're transforming a single instance together. So let's say you have a bouncing ball that you're changing the transformation matrix of, but the individual vertices of the ball are not changing. In that case, you would have the ball itself as an instance, and your transformation matrices are updated as part of an update to the top level build. The cases where you would update the bottom level build are where you have perhaps vertex skinning or anything where you're actually animating the mesh itself. Then you'd want to do an update on the bottom level structure. Something to keep in mind, the further you drift away from the original build, the lower potentially your ray intersection performance is going to be. So whenever you drift too far, you should kick off a full rebuild. And this can be done in the background on the async compute queue. So you can actually do this whenever you're not doing other work to opportunistically bring your performance back up. So a quick recap of acceleration structures. Comprised a fundamental unit of geometries. Geometries are grouped together to form bottom level structures. Once you've built those bottom level structures, you can throw away the original geometry. And then instances of those bottom level structures are grouped together into a top level structure. And again, you can have multiple of both of these types of structures in your title. Typically, you're going to have many bottom level acceleration structures and a couple top level structures. And together, the top level structure itself then represents the entire scene. So now we've gone over how we represent the scene itself using DXR. Let's talk about how we actually trace rays into the scene and get the intersections. So this is done with a new command list API called dispatch rays. It's very similar to compute. You dispatch a 2D grid of threads, and then from within those threads, you can emit any number of rays from 0 to n using the new trace ray intrinsic in HLSL. Now, you can emit any number of rays, but a good starting point is one trace ray call per thread. After you call trace ray, you will get your results back, and I'll go over in a minute how you do that. But there is no, unlike the rendering pipeline where you have a render target output bound to the pipeline, this is much more similar to the compute shader pipeline where there's no explicit output. Instead, you write your output using UAVs. So this is the trace ray intrinsic. It has the properties that you would expect, an origin, a direction, as well as a floating point Tmin, Tmax that specifies what range of intersection you'd like to consider in the scene. In addition, it also has this application-defined payload structure. This is a payload that follows the ray as it executes the various shaders in the scene. And the benefit of this is that it's a relatively tightly scoped structure, so you can the implementation is free to optimize and keep the payload structure very tightly coupled to that ray without blowing out caches or anything like that. So one thing you should do is be sure to keep your payload relatively small, a couple of bytes. You don't want a kilobyte payload. So once you've called trace ray, how are intersections determined? Well, this depends on the type of geometry that you've specified. So for a triangle geometry, the determination of intersections is automatic. It's what you would expect. If the ray intersects the triangle, then it triggers an intersection. The attributes themselves you get back within the shaders are the barocentric coordinates of the intersection. There's no built-in interpolators, but using the barocentric coordinates, you can look up into an SRV buffer and do the interpolation yourself. For programmable geometry, the intersection is determined by what's called an intersection shader. Now, in intersection shader, those are invoked whenever a ray intersects the axis line bounding box, and then it's up to the application to specify whether or not that ray actually intersects your custom geometry, or whether or not it just missed. And then as well, whenever you have the intersection point, the application specifies its own attributes. They can be barocentrics if it's a triangle-like structure, but otherwise you can specify attributes however you like. You should also make sure to try and keep this small, though, a few bytes. Now, before I go on and talk about more shaders, I should mention that everything I'm talking about here and pretty much every new feature in DX12 requires the new Dixel compiler. If you're still using FXC, you should go get the new one. Something to keep in mind, though, for DXR specifically, you should use the pre-built binary that's in the experimental SDK, which I'll link to later. But for everything else, you should use that link. It's on GitHub. You can compile it yourself. There's also pre-built releases. So now we've talked about how we trace rays into the scene and get intersections. Now let's talk about how we actually figure out and execute the material shaders. So once an intersection is determined, the material shaders themselves are called hit shaders. Now, hit shaders are invoked whenever you have an intersection with geometry, whether that's triangles or procedural geometry. And within the hit shaders, you have access to the intersection attributes, or triangles, barocentrics, for the custom ones, whatever the application defined. It also has read-write access to the ray payload. And then from within these hit shaders, you can call trace ray to do recursive ray traversal, for example, if you want to do multi-bounce lighting. And there's two types of hit shaders in DXR. The first one is called the any hit shader. And this is invoked for all intersections along a ray path from Tmin to Tmax. You're allowed to read the attributes, and then you can read and modify the ray payload for subsequent shaders. So you'll have multiple invocations of any hit shaders, and you can modify the payload as you go along executing them. The intention for this is that if you have, say, transparent geometry, you can accumulate, say, the partially transparent color into the payload, and then process additional any hit shaders until you finally get to one that you determine to be opaque. There's two intrinsics that you can call within these shaders that are relevant. The first one is ignore hit. That basically means, okay, stop executing the shader. I'm not going to contribute anything more to this particular intersection. The next one is accept hit and end search. That will actually prevent any subsequent any hit shaders from being invoked. This is useful, for example, if you don't particularly care about the intersection attributes themselves or doing anything with it. You just care if there is a clear path or not between 2 points, for example, for shadows. But once you've executed all of your relevant any hit shaders, once you've executed all of your any hit shaders, the closest accepted intersection, which is the one you've let run to completion without calling ignore or terminate, the closest accepted intersection executes the closest hit shader. Within this, you can read the attributes. You can also modify the ray payload, and that will be visible finally to the call site where you originally called trace ray, for example, in the ray generation shader. And of course, you can cast more rays from this point as well. Now, one additional shader type that we have, if no accepted intersections occur within the trace array call, the miss shader is instead invoked. You have that's if no intersections occur through Tmax. From there, you can trace more rays, for example, into a lower LOD structure. So you can have, for example, a very tightly bound high detail acceleration structure representation. Then you can have a much wider one that's lower detail. So you could continue the ray basically with that lower LOD structure. Alternately, you could do something like return transparent black or sample the skybox. So now that we've talked about how the shaders actually run, how does the implementation actually figure out what shaders you want to run? Something that's a very unique challenge for ray tracing is that when you construct your scene and trace a ray into it, you don't know what geometry it's going to intersect. So a particular intersection could potentially require any geometry, need any shader, or need any resource. Now, for the resource side of things, when we first released DX12, we had the concept of bindless resources. So that solves that problem. It's essentially a large table that's dynamically and arbitrarily indexable within shaders that you can say, OK, this is texture 515, so I'm going to go use that texture. What we don't have for today is bindless shaders. That's for dynamically indexing based on material. Well, with the XR, we do have a solution for this, and it's called shader tables. So what is a shader table? A shader table is a GPU buffer that is comprised of individual shader records. A shader record is comprised of a shader ID and a set of root arguments. Now, every time you execute a shader in the graphics pipeline, you have your root signature. You have your shader code, you have your root signature, and then you have your root parameters that go into that. So the shader tables allow you to specify those shader arguments and the shader itself. In DXR specifically, it's very flexible. You have many options for how you specify what record index you use for a particular intersection. There's many different ways to do that. I won't go into details, but suffice to say, whatever configuration you'd like to use, there's a way to specify that in the API. Now, the shader IDs themselves are acquired from a new API concept called a state object. Now, state objects are not entirely new. You can think of them kind of as PSOs v2, it's pipeline state objects v2. It's a set of shaders and root signatures. And unlike for example, the graphics pipeline state or the compute pipeline state today, state objects are meant to represent a very generic form of pipeline state. So you could imagine a world where you're representing either your graphics pipeline state, your compute pipeline state in a state object. For now, state objects just represent ray tracing pipelines, but they're also designed to be able to support future pipelines as well. How they function is you essentially associate a Dixel library, and you define the exports on that library within the state object. You can then create pipeline-specific state sub-objects and associations with those. Finally, once you've compiled those state objects with the driver, you can get the state object properties interface to reflect data back about those state objects, for example, the shader IDs. So let's talk about ray tracing state objects specifically. There's various properties of the ray tracing state object. You can configure the maximum ray recursion depth. You can configure your maximum payload and attribute size. And this also allows you, this is also the mechanism by which you specify your individual hit groups. Now, rather than specifying an individual shader ID for your hit shader, your miss shader, your any hit shader, instead we've decided to group these into collections of these shaders called hit groups. You can think of a hit group as basically all the information that you need to figure out what to do when you have an intersection. So a hit group is comprised of, optionally, an intersection shader, an any hit shader, and a closest hit shader. Now, you can have all of them, you can have none of them. Having none of them wouldn't really do much, but you can. So you use whichever ones you need, and then you compile those together, and then get the shader ID from them from the state object properties interface, and then you place that into your shader table as the ID. So in addition to the hit groups, you also have the ray generation shader ID, as well as the miss shader ID. And together, those three objects are part of the argument to the dispatch raise call. So we've gone over all the various pieces of how DXR solves problems with ray tracing. So we have a scene geometry representation through acceleration structures. We can trace rays into the scene and get the intersections through dispatch rays and the trace ray intrinsic. And we can determine and execute material shaders using shader tables and state objects. So putting it all together, just in summary, this is how you use DXR at a 10,000 kilometer level. You first want to start by creating your stated objects with a set of potential material shaders. You then create a top and bottom level acceleration structures to represent your scene. Then you'll create your shader table with those individual shader records and shader IDs with the root parameters, where you've acquired the shader IDs from the properties interface on the state object. Finally, once you have all that set up, you call dispatch rays, which invokes the ray generation shader, and in turn calls trace ray. Finally, those values are returned to the ray generation shader itself. You can write the results out to a UAV, and finally, you can incorporate those UAV results into your final scene render. So now let's talk about tool support. I'm very excited to say that from day one, as in today, you can go download it. We have PIX support available. If you want to learn more about PIX, you can go see this room tomorrow at 12:45. Sean is going to be talking about some of the other new features that we have in PIX. We also have a tool called the fallback layer. This is an open source implementation of DXR that you can, it's compute shader based. It does require a Dixel supporting driver, but otherwise it does not require any hardware driver support for DXR, so you can use this to experiment. Finally, we have a tool called VSPS to hit group conversion. This allows you to take a pair of vertex and pixel shaders and convert them into a hit group, so you don't have to completely reauthor your shaders into proper hit shaders. This tool does not, it's not in the SDK yet, but we're hoping to ship it soon. Finally, we have the ray tracing helper header. So something to keep in mind about state objects, they're extremely verbose. The ray tracing helper header, which will probably be integrated into D3DX12 eventually. For now, it's a separate header, but you should definitely use this when you're constructing your state objects. It gives you a much tighter binding of the ray tracing pipeline representation. So it's much easier to program to than the native API. Just to show you an example of the tools. So this is some of the really awesome work that we've done with PIX support for DXR. So this is a capture of an internal demo that we have. And we have a number of interesting new features specifically for ray tracing. We have a visualization of state object trees. I'm really glad that we have this now because when I was first doing DXR, I spent like an hour writing my own pretty printer in C++ that told me the state object tree because I kept getting it wrong. But now it's in PIX, so you don't have to do that yourself. In addition, we have visualization of the shader tables themselves. So for a particular dispatch ray call, you can look and see what are all the root parameters, what are all the shaders that you're actually bound to the pipeline at this point. And then finally, we have the visualization of the acceleration structures themselves, which is very helpful because this stuff is very new. SDK layers is not 100% there yet, so you're very likely to make some mistakes. So being able to have visualization here and see whether or not what you're actually rendering makes sense is going to be very helpful. So with that, I'll hand it over to Johan, who's going to show you some of the really awesome work that they've done with DXR.
Thanks, Matt. Yeah, so I'm here today together with Colin Barber-Brisbois in our team at Electronic Arts in a fairly new group called SEED that I run. So our group is we're essentially a research division of Electronic Arts where we try to explore the future of interactive entertainment, whether through new technologies like ray tracing that we're going to talk about today, or new type of creative use cases of technologies or different type of ideas there. And we've been looking at ray tracing for a little bit now, got an early version of DXR that we've been testing, giving feedback to Microsoft and to other vendors. And cutting it short, I'll just show you a video. Thanks. So that was some fun work we've been doing in the last 2 months, essentially. We call this project Pika Pika. I picked that codename, it's a weird one. It means a European magpie. Our codenames are birds for some reason. But anyway, this is a small minigame that we built. And actually, it's not a minigame for humans. It's a minigame for our self-learning neural network agents that we're talking a little bit more about on Thursday in the 11:30 session call about deep learning. So we built a small game for these agents to play around with in an interesting environment. We have our own small, fairly new research engine, essentially, also that we do these creative and technical experiments in, also called Halcyon. It's not a full game engine. It's more like a small framework for us to be able to do these experiments fairly quickly. And some of our goals with this project was to, well, first of all, to explore different types of ray tracing techniques together with DirectX Raytracing and that new API, and create something with very clean and consistent visuals. Well, I've been working on Battlefield for a long time in my career, and other people come from other types of AAA games, so it's really refreshing to try and create something super clean and simple visuals in that sense, but still make it look really good. And this scene is actually also fully procedurally assembled and generated. There's some manually created assets as well done by good artists, but we have tons of different variations of these scenes for our AI agents to be able to explore different type of environments and not sort of fit for a specific environment. And another core important goal for us was that we didn't want to do any pre-computation. We didn't want to bake any light maps or pre-compute any type of offline acceleration structures. And we didn't want our artists to have to play specific local reflection volumes or do anything beyond creating awesome art and make it automatically look good. So that was our goal for this project. And we choose to use ray tracing for this. It happened to align very well timing-wise, but it's a technique we've been super interested in general, of exploring different type of avenues of getting to high-quality visuals, but also to simple workflows. So for us, ray tracing is a really flexible and just a new good tool in our toolbox of different type of techniques that we're using. And you'll see a little bit more of that later in this talk of like how we're combining different type of approaches here. But ray tracing specifically is really great for solving these type of sparse and incoherent problems, like what Matt was talking about before of reflections and a whole bunch of other different techniques. Rasterization is awesome for large brute force rendering of large viewports and tons of things, but there's so many techniques where it's not really appropriate. And at this specific time, when you have this, I can't stress enough of the importance of having an actual unified API and how much that helped us, where we can do both graphics or rasterization and compute and ray tracing and have it all fitting together. We were a bit curious about other types of APIs or ray tracing frameworks like optics and other things before, or building something ourselves, but it's kind of complex when you have to interop in tons of different type of solutions there. And then, so that's the DXR unified API there, and also all the work NVIDIA's done on RTX and sort of this ray tracing core to implement that efficiently. And simply, ray tracing gives us very high quality visuals and a very easy way of getting to ground truth visuals as well for reference. So what we choose to build, there are many ways of using ray tracing, of course. You can augment an existing pipeline, you can do full ray trace all your visuals, you can do path tracing. We have some path tracing as a reference mode I mentioned, but we also are doing, we wanted to get something that can run in real time. Well, our agents required it, but we want to do interactive visuals. That's an entire goal. So we choose to build a fairly hybrid rendering pipeline combining different type of techniques. So to start, we're using classic deferred shading, which is rasterization operation of rendering out the G-buffer. And once we have that G-buffer, we can calculate shadows based on the depth buffer, essentially from that. And that can either be a cascaded shadow map implementation, and we have one, and not a particularly good one, but we have one, or we can ray trace it, and we choose to ray trace it in this specific scene. And then we calculate lighting as well, and that's a standard computer. Actually, in this scene, we mostly have one light source. It's a very, very simple one, but you can do tile-based lighting or clustered lighting or any type of approach there, but through compute. You can technically ray trace that also for more advanced shadows, but just for direct lighting, it's usually enough for that. On the other hand, though, reflections. That we went fairly in depth on implementing using ray tracing, and Colin will be talking a little bit more about that in depth just after me here. And once we have those components, well, there's another component also missing, which is global illumination for our scenes. So usually this is something that's pre-computed, and it's actually something that's very complex to calculate through raster. I've done it before a long time ago, of like rendering out Hemi cubes and distributed across light map pixels in scenes, but it's usually a fairly complex operation to force into a raster operation. So we have a fairly interesting approach that we'll be talking actually 5 o'clock later today in our other session. That's a dynamic surfel GI sort of progressive rendering technique that uses ray tracing to calculate irradiance for dynamic surfels in our environment. And ambient occlusion, that's standardly done through screen space techniques, but can also be ray traced at much higher quality, and Colin will go through that a little bit more here as well. And we also have a technique for doing transparency and translucency. So this is kind of tricky to do through raster, especially when you have this type of scattering techniques in translucency or this order-independent nature. So we ray trace that and ray trace it in texture space. And then finally, post-processing. So we're rendering out an HDR picture, and all of our post-processes are actually compute, so depth of field and motion blur and the standard HDR tone mapping, all of those things. So we had a fairly high-level hybrid pipeline of combining all of these different things, and that was one of the main things that we wanted to explore, like what works well for these different type of cases. And we're definitely not done yet, but for this specific demo, we found a pretty good way of how it all fits together. And I actually want to show that directly. Hopefully it doesn't crash. So if we press that button, boom. So this is our small demo. This is a sort of a static version of the scene, so it's easier to look at different visuals. So this is running on a single Titan V, which is a GPU that probably very, very few people have, because it's a very expensive GPU that NVIDIA doesn't have that many of yet. Hopefully they will build more and cheaper ones. So this runs at around 60 FPS at 1080p, and we have all of these different type of techniques interacting here. So we have the nice soft shadows and some reflections, and it looks kind of subtle. We didn't want to just create mirrors everywhere, although for our videos, of course, we had to have some mandatory reflective spheres as well. So it's a kind of cute, small environment, and you can get some of these kind of interesting technique or interesting visuals, kind of subtle, but like, you wouldn't get this with SSR, actually seeing the reflection behind you, what Matt was talking about as well. And if we switch to, for example, our reflection mode, you can see it even more clearly. Let's see, where is it? There. So there's a normal map on the surface back here, so that's why it's a little bit distorted, artistic choice. And you have tons of these different details. And this, we were really happy of how things sort of ended up everything just fitting together. And actually, one of the most important things for using this combination of techniques for us was that it enabled us to create really consistent visuals, because we don't have these various types of artifacts you get with SSR or with cascaded shadow maps. Everything just fits together. So our artists were just throwing in art, and everything just looked awesome and cute. Even this like tiny button here and this tiny screw up on top of it. And the combination of shadows here, for example, this little bit larger object had these contact shadows, becomes a little bit softer, and they fit together nicely also. And we can tweak things dynamically and just see. Of making sort of softer shadows or increasing or making harder shadows, and just completely dynamic, interesting, small, nice environment. And now I think Colin will talk a little bit more details about these things.
Yep.
So switch back. There we go.
Cool. Thanks, Johan. Mm-hmm. Yeah. So demo's super cool, but and going back a bit to what Matt was saying earlier on about how DXR works. I just want to give you guys a bit of an overview of how this demo is set up with the new DXR concepts, but really quickly. So first, when we spawn a mesh, we build the bottom acceleration structure for it. So the API, like as you saw in Matt's talk, the API allows you to specify multiple geometry types, but for the demo, we mostly use triangles. And once the bottom acceleration structures are built, we specify meshes, instances, and those are specified in the top acceleration. They basically represent a mesh at a specific position and a specific orientation with that matrix. And so when a mesh moves, well, we need to update its instance matrix in the top acceleration. And so in the demo, as you mostly saw with the little robots, and you'll see it a bit more later if you come to the NVIDIA session, we update the accelerations, the top acceleration structure every frame. It's really fast because actually it's just pushing new matrices every frame, and you're actually not rebuilding A, B, Bs from triangles, unlike the bottom one. And so once all of this is done, we can spawn some arrays, right? So we have many types. We support many types of arrays for all of our techniques. We have per instance hit shaders for all the array types. So primary, shadows, for example. We have global mesh shaders. And all of these shaders, sorry about that. So all of these shaders need to live at a place that's global, and so that's why they live in the shader table. And by living in the shader table, they're accessible for all arrays launched in the scene. And so the first technique I want to cover today is the way we handle reflections in the demo. And so, like Johan mentioned, we took a hybrid approach where we first rasterized primary visibility. We launch rays from the G buffer. And all of this is done in half resolution in 2x2 blocks, but obviously you can do this in full screen if you want. Once this is done, we do a spatial temporal reconstruction at full resolution. And so, from the image to the right, you can see how ray trace reflections just add so much and just work for all types of surfaces. And our first approach, actually, we combined it with SSR for performance, but in the end, to make sure everything matches with roughness, it was just easier to do ray tracing for simplicity. And so here's a breakdown of how we launch rays. So to the right, you have some HLSL pseudocode. I kind of simplified it a bit. It doesn't compile, so please don't use that directly. OK, so first what we do is we select one of the 2x2, one of the 2 pixels we want to trace. And then we reconstruct the positions and the vectors, obviously, from the G buffer. We initialize our low discrepancy Monte Carlo Halton sequence and a random number sequence generator that we're going to use to rotate the Halton sequence. We initialize the payload. We prepare a new ray. And where is it? Yeah, so we specify, like Matt said, you specify origin, direction. We specify direction based on some material properties, actually. But I'll cover that in the NVIDIA session, because that's a bit much for this session. We then trace. And then we gather the results from the payload. And so for the temporal filtering, for the reflections, we gather not just the color, but also the ray direction, the ray length, and went over the PDF. And so once we've generated the half-resolution images with the hit results, we use them to synthesize the full resolution output. So for every pixel in the full resolution image, we use 16 samples from the half-res data. Neighbors from high-res pixels obviously provide useful information, but you have to be careful to not make it obvious that you reuse ray trace results, especially going from half-res to full res. And so for that, we use blue noise to break the sampling pattern. And so that way we make sure that in every 2x2 quad, all pixels have different hit results. And so this part provides the spatial part of the filter, which we couple with a temporal component similar to TA. And at the end, we have a second stage, larger variance-driven bilateral filter that we use to clean up the remaining noise. It's especially useful for the rougher reflections. And so on the right, you see the raw, I guess, unfiltered output, and to the bottom, that's the filtered output. And so this is what the world looks like if it was fully reflective, so basically the worst case scenario. With ray tracing, especially when roughness is handled properly, reflections become so grounded and well occluded, and it just looks really nice. And so let's zoom on some details and compare. So to the left, you have pretty basic SSR. I think Tom put this in like one night or something like that. And in the middle, you have our ray trace G-buffer reflections. So as you can see under the robot on the ray trace reflections, which obviously you can't see on SSR because that info is just not there. And so to the right, you can see how this compares to our path trace reference. So we actually have a full path trace reference for everything we do to make sure we compare with ground truth. And so if you squint a bit, you can kind of squint the path trace noise away, and you can see that our approach is actually quite convincing. Here's another example that compares the 3 techniques. With our approach, stuff definitely feels more grounded, and there's almost no sampling artifacts, especially noticeable on the paperclip there at the top. I mean, results look pretty close to path tracing, so that's really cool. Obviously, another technique that maps and scales well to real-time ray tracing is obviously ambient occlusion. So, since ambient occlusion is the integral of the visibility function over the hemisphere, we get more grounded results because all the random directions that we use during sampling actually end up in the scene, unlike with screen space techniques, where rays can go either outside the screen or just the hit point is just not visible. And so let's look at some results. So this is a basic screen space AO. Looks pretty good. But this is ray traced AO, which obviously looks much more grounded. And if we zoom in a bit, what if we used similar ranges for screen space AO and the ray trace AO? So here's the screen space AO. Notice the broom against the wall. It's got some really nice darkening there. And then if we switch to ray trace AO, you can see how the missing information from, I'll toggle between them actually so you can see better. You can see how the missing information that you get with ray trace AO makes it so that everything looks much more believable. And if you look carefully, you'll notice that the broom is actually not touching the wall. So the ray trace AO exposed some imprecisions in our procedural placement, which SSAO kind of hid. So that was kind of a funny find. But that's part of game dev, I guess. And what's cool about ray trace AO is you can go even further and have some kind of far field AO. So this is with a bit more wider ranges. And so for our demo, we also explored doing ray tracing on MGPU. Our approach, where the primary GPU basically acts as an arbiter, and it splits the work for secondary devices, and it does the final work. It finishes the final work basically with the filtering. And so here's how it works. So if we take this scene, we split it up. So first we run the ray generation. Did I accelerate everything? Okay. Oh, it's all in one. Well, anyways, so we run the ray generation on the primary GPU for the entire screen. Then we copy ray generation results in subregions to other GPUs. So like I said, the first one is the arbiter. Then we run ray tracing phases on the other GPUs, so just basically a subsection of the screen for each GPU. We copy the tracing results back and then we do the filtering on the main GPU. And basically this allows, by doing the filtering on the first GPU, allows us to mitigate temporal problems. And that's what I had.
Yep, and just to wrap up a little bit, we feel like this is just the beginning. Well, it's literally the beginning. It just got announced. But it's an important new tool going forward for us, and I think for a lot of other people. The unified API in DX12 with this have been a great success for us. It is quite a lot of different stages and things how you fit it together, but it was easier than we thought to really connect everything together, and it's been working really well. Super awesome to sort of experiment with and integrate and convert to different type of techniques and fit into the rest of our small engine in that sense. On the more interesting side, though, I think like the main thing that we ran into was like with ray tracing and with trying to make things a little bit more sparse, we run into these fairly complex but flexible trade-offs of like, do you want noise or do you want bad performance or do you want ghosting or how do you want it, what's the right trade-off there? In this specific scene, it's actually a little bit easier for us because it's mostly opaque in the scene and not that much stuff is moving in it. So our temporal reprojections worked fairly well and we were able to tweak our reduce ghosting to be, sort of working well in this type of scenes. Going forward, we'll probably try a lot more complex dynamic geometry scenes and with many more things moving, and we'll probably have to make different type of trade-offs there. Perhaps some stuff move back to raster, and some things will take even more performance through ray tracing in that that sense. But we did get to really high-quality visuals. Really happy about that. But there's a lot more things to look into. Performance here is really quite early, both on our side and on the vendor sides in this. We do want to look into even more sparse techniques of figuring out how can we ray trace only where it's fully needed, essentially, and adapt the workloads across the frame, essentially. Shadows is a good example of that. It's only in the penumbra where it's really interesting to get ray trace results. In the middle of a shadow or when it's just empty space, why are you throwing rays at all that? So trying to figure out those things based on acceleration instructions and things like that. Cool. So that's a little bit just high level. We have another talk, as I mentioned, just after this, essentially, that goes a little bit more in depth and also shows some results in Frostbite as a workflow that team has been working on. And as I mentioned, we have a deep learning talk tomorrow as well, and a procedural talk tomorrow as well of how this world was built and assembled, this small, cute world. And thanks to a lot of people in our team, and NVIDIA and Microsoft. Yeah, that's our group. I think Matt will finish it off. Oh, yeah.
Check, check. OK. All right. So a lot of cool stuff, DirectX Raytracing. How to get started. First, get on Windows 10 and sign up for the Windows Insider program. It does require RS4 builds if you sign up for the Windows Insider program. Fast builds, not the skip ahead builds. You'll be able to use this stuff. You do also need the experimental SDK. That includes specs, samples, headers, libs, binaries, symbols, everything you need. There's also a special build of Pix that supports the ray tracing stuff. Finally, there's an overview of DXR. This is our blog post. If you only remember one URL from this slide, it's going to be aka.ms/DXR. That'll point you to everything else. And then also, when you start using this stuff, please do give us feedback on the DirectX Tech forums. We actually do read that stuff, and there is still time to make changes to this API before it goes live later this year in a retail sense. So yeah, go download the SDK and start experimenting today. And a quick shout out to the folks at NVIDIA are putting together a ray tracing gems book. So if you are interested and if you have papers or good ideas for ray tracing, there's some information here. Deadline for submissions coming up fast. So if you have anything you'd like to contribute, go to that site for more information.